Hello, dear Professor Hassan Al-Hajj Ahmed. I hope you are well. My name is Muhammad Jamil Sleet, and I am a student in computer science at the College of Information Technology. I am currently studying operating systems with you, and I am delighted to be a student in this course, given its critical importance in developing my knowledge and skills in my future studies and work. I strive to make the most of this course and apply what I learn practically. I hope you will accept this assignment, and I look forward to your valuable feedback, which will help me improve my academic performance. Thank you for your time and effort, and I wish you continued success. Exploring the concept of mutex mutual exclusion in operating system. Definition of mutex. A mutex, short for mutual exclusion, is a fundamental synchronization primitive used in operating systems to control access to shared resources in a multi-threaded or multi-process environment. It ensures that only one thread or processes at a time can access a specific section of code or resource, commonly referred to as a critical section. The primary goal of a mutex is to prevent race condition, where the outcome of operating depends on the unpredictable timing of threads, leading to inconsistent or incorrect results. Rule in process synchronization. Processes or thread synchronization is essentially in environments where multiple processes share data or hardware. Without proper synchronization, concurrent access to resources may lead to data corruption, unpredictable behavior, crashes. A mutex acts as a lock. When a thread wants to enter a critical section, it attempts to acquire the mutex. If the mutex is already held, the thread is blocked. Waits. Once the thread completes its tasks in the critical section, it releases the mutex, allowing the next waiting thread to process. This ensures that only one thread can execute the critical section at any time, maintaining data consistency and system stability. Preventing race conditions. Race conditions occur when multiple threads modify a resource resource without proper coordination. Example: two threads increment a share counter. Both read the value 5 at the same time. Each adds 1 and writes back 6. The final result is 6 instead of the expected 7. Comparison with related synchronization mechanisms. Feature: mutex, SIM4 spin lock. Value range: ownership, blocking, use case, CPU used. Summary: a mutex best for mutual exclusion where the thread should wait without consuming CPU. Semaphore: good for managing multiple instances of a resource. Spin lock: in instances where locks are held for very short duration and context switching is more expensive than busy waiting. Real world analogy: a single ATM machine. Example, in a single ATM machine. Imagine there is only one ATM machine at a bank branch. Multiple people want to use it, but only one person can use the ATM at a time. Here's how this relates to the concept of mutex in operating systems. Real world operating system concepts. Real world, only one person can use the ATM. Operating system concepts, only one thread can enter the critical section. 2. Other wait in line, other threads are blocked or waiting for the mutex. 3. Person finishes and leaves, a thread release unlock the mutex. 4. Next person uses the ATM. Next thread acquire the mutex. How this shows mutual exclusion. The ATM is the shared resources. The person using the ATM holds the mutex lock. The queue of people represents waiting threads. No two people can use the ATM at the same time, just as no two threads can access a critical section, guarded by a mutex simulationalism. Key takeaway. The ATM example makes it clear that mutual exclusion ensures orderly and exclusive access. Without such a system, multiple people could try to use the ATM at once, leading to chaos, just like race conditions in software. The mutex ensure fairness and consistency, just as ATM queue ensure everyone gets their turn without conflict. Programming task. Mutex in Java show the out version without a mutex, resulting in unpredictable or incorrect outcomes due to currently access. The example in the program NetBeans. Final counter value without mutex. Fixed verging using mutex. Fix the issue by applying a mutex, ensuring correct and consistent results. Final counter value with mutex. Problems and advanced concerns. What can go wrong with the mutexes? Deadlock. If two threads wait for each other resources, they can block indefinitely. Priority inversion: a high priority thread is blocked by a low priority thread holding the lock. Starvation fairness issue: some thread may never get the lock if others keep grabbing it. How to mitigate these problems? Problems and solution. What could go wrong if mutex is used? The schedule is the schedule is explain the wrong. Advanced synchronization concerns. Deadlocks occur when multiple threads are waiting for resources in a circular chain. Example: thread alloc mutex 1, then waits for mutex 2. Thread B locks mutex 2 and waits for mutex 1. Neither can processed. Mitigation strategies. Lock ordering: always occur mutex in a predefined order. Time out: allow thread to give up trying to occur a lock after creation time. Deadlock detection: use algorithm to detect cycle in the resource graph and take corrective action. Advanced synchronization concerns. Fairness violation strategy. Mutex implementation may favor certain thread. Magnetization strategies. Best practices for using mutexes. Keep critical sections short to reduce lock continue. Avoid nested locks unless absolutely necessary. And if used, enforce consistent lock execution order. 3. Use timeouts or try locks where possible to avoid indefined waiting. 4. Prefer higher level concurrency tools. 5. Test throttle under concrete loads to catch subtle timing bugs. Summary of learning: mutexes are essential for ensuring current in multi-threaded programs. 2. Without proper synchronization, even simple operating like incrementing a counter can go wrong. Proper use of mutexes can prevent race condition, but care must be taken to avoid deadlocks and performance bootlinks. For real-world analogies help bridge the conceptual gap between theory and implementation.